So far this semester, we've covered chapters 1 through 4, and we've looked at the specific application of limits to finding derivatives, which we use to understand tangent lines and their slopes and various applications for that. But as we turn our attention now to chapter 5, we're going to shift our focus instead to using limits to do something new, specifically to help determine areas of kind of awkwardly shaped regions. Now, we're going to see how exactly we can use this and why exactly it's going to really be important or relevant to actually be able to compute areas of regions. So to start off with this beginning general idea, let's see what we have here. A car is traveling at a constant rate of 50 miles per hour for a 2-hour period. I'm interested in finding the total change in the position of the car, and I want to represent this quantity as an area on a graph. Okay, now, first off, I can easily answer the first question that's posed here. If a car is traveling at 50 miles an hour for a 2-hour period, find the change in position? Essentially, I'm asking, how far did it go? If a car travels 50 miles an hour for 2 hours, well, then obviously it went 50 miles in the first hour and 50 miles in the second, so it went 100 miles. So I can start off by saying here that clearly I can see that if I was to go 50 miles per hour times 2 hours, I'm going to end up with a grand total of 100 miles. But the interesting part here again is that I can actually see that it's possible to represent this in a picture. So let's suppose that I was going to go ahead and work with a set of axes here. Let's suppose that my horizontal axis here represents time, and that my vertical axis here represents velocity, like this 50 miles an hour. So I'm going to go ahead and I'm going to draw a function up here, but this is going to be a function that's going to model the car's velocity. Now, since the car is traveling at a constant rate of 50 miles per hour, I can imagine putting 50 miles per hour right here on my vertical axis. And since the car always travels at this speed, it's just going to be moving like this. That's just some constant flat value of 50 miles an hour all the time. And I, of course, have the same curve stretching out towards the other direction as well. But now I can start to see that on the horizontal axis, if I marked out where 1 hour is and then where 2 hours actually occurs, then I can really easily and quickly see that in here, if I was to say, well, my car is going to travel from 0 out to 2, then notice that if I was to look at this space kind of covered in here, that is the space that's underneath the curve, underneath that velocity curve, but also that is occurring between 0 and 2, then I can see that this kind of represents graphically exactly the concept that I had here. I have 50 miles an hour being measured as this vertical distance. I have 2 hours of time being represented as this horizontal distance. And so 50 times 2 makes an area of 100 miles. So again, I can state here, notice that the shaded region is 50 miles per hour times 2 hours. And so, of course, the amount of shaded space that I have should be should be 100 miles. So this is kind of the idea of where we're going to be going in Chapter 5. We're going to see that the reason that we're interested in finding areas under curves is because areas under curves could actually represent some sort of real-world quantity that we might be interested in computing. Now, obviously here in this opening example, I didn't really need this picture to answer the question. But if the question starts to become significantly more complicated, then representing the thing that I'm looking for as an area under the curve and finding interesting ways to calculate it might be a really good way to tackle or approach the problem. So the note that we can kind of make here at this point is that when we have a rate of change of a quantity that's positive, that is like here, the position was changing for this car at a rate of a positive 50 miles per hour, Then we could measure the total change in the quantity. That is, we could figure out how many miles were moved and represent that as an area between our function, between the speed of this quantity changing and the horizontal x-axis. So this note is really just saying that it doesn't matter whether I'm dealing with miles per hour and tracking a number of miles. I could also be working with, say, I don't know, tons of pollution produced an hour by a large factory. And if I could set up the same thing, if I could model with an equation how quickly this pollution, say, per hour if I could model it with some sort of a function, then I could easily go ahead and find an area under it on a given interval to make a total change of, or to figure out a total amount of pollution produced. Well, let's take a look at some other examples here to kind of get the idea of what are we going to do if I don't have a nice, simple, like basic rectangular region. Well, let's take a look here at general idea part 2. Let's suppose we kind of have the same sort of basic idea as what we had up above. Well, imagine that we have an object that's moving. So let's say that an object is traveling, but now it's not traveling at a constant rate. Now it's traveling at a speed that keeps changing over the course of time. It's traveling 1 over t plus 1 feet per second. And we're going to be interested in measuring this object between the time of 1 and the time of 3. Maybe those would have to be here in seconds. And what we're going to be interested in doing is estimating the total change in the position of the object during this time. So there's an object that's moving according to this kind of velocity formula here, and we're interested that if we started watching the object at time 1, at the 1 second mark, and we tracked it all the way until the 3 second mark, how far did it move? Well, if you were to take a look at what we have here in this picture, you can see that right here I have a picture of my v of t curve. Kind of like up here, I had sketched a picture of my velocity for the car. And so I can see again that as my value of t continues to increase, my object is going to be slowing down, right? Because as t gets larger, my denominator gets larger, produces a smaller overall value. At the time of 1 second, I can see that I'm going to be moving at 1/2 feet per second. That's what I see here in the picture. By the time I get all the way up to 3, I'm moving at 1/4 of a foot per second. So how in the world am I going to go ahead and try to find this area? Because what I'll notice is that it should represent the total number of feet. I have seconds down here, and I have feet per second in this vertical direction, so the total amount of space should represent a given amount of feet. So I'll start off by just identifying here that calculating the area of this yellow space is difficult because there's not this isn't a nice geometric shape. So it's not like I can do something as easy as what we did up above, which is just like, height times length and just boom, instantly be done. But here's what I'm going to do to maybe try to slowly tackle this problem. I'll say that we can break up the interval of 1 to 3 into smaller subintervals, and then approximate the change in position on each interval using the area of a rectangle. All right, so there's a lot of information there, but let's go ahead and take a look at what I mean by this. So let's suppose I take my picture here, and I'm going to start to break it up into some different pieces. Now I'm going to go ahead here, and let's just suppose that I'm going to break this up into 4 smaller intervals. So I'm going to imagine creating an interval that goes from 1 to 1.5. So I can imagine an interval that occurs right here. I'm also going to create one that goes from 1.5 over to 2, from 2 to 2.5, and then finally from 2.5 to 3. So I kind of have four kind of intervals that are being sketched in here. And what I'm going to do with each of those intervals is I'm going to create a little approximation of how much yellow space there is, say from 1 over to 1.5. And to do that, I'm going to go ahead and I'm going to draw in some different rectangles. Let's see how I could do this in the first instance. So let's consider the interval from 1 to 1.5. Now I'm going to start here at the right edge at 1.5, and I'm just going to draw a vertical line up until I hit my function, okay, right there. And then I'm going to draw a perfectly horizontal line coming across, and I'm going to come back down. And what you can see here is I've generated this blue rectangle. And that rectangle has an area. In fact, I could probably find that area without much difficulty whatsoever. And I could tell that then the area of the blue space is almost equivalent to the area of the yellow space on this interval. It looks to be a little bit less, but it would be pretty close. Notice though I could repeat this process for each individual interval, going from the right side all the way up, then drawing a horizontal line over. I'll do it again, drawing from the right side up, and then finishing off with a nice horizontal line and getting a rectangle. As you can see, when I take a look at the amount of yellow space that I'm going to ultimately end up not including here, there's very little yellow space that's not accounted for. But the good part is that I can find the area of each one of these individual rectangles pretty simply. Let's see what we would be able to do with this. So what we would say is that the total amount of area that's under that curve could roughly be equal to finding the areas of each one of my different rectangles. So let's start by writing out the area formula for the first rectangle. I would notice that if I can do the width times the height, I'm going to be in good shape. So I'll notice here that my height is going to be, well, I guess it's kind of however tall the function is right here on this edge. But I could figure out how tall that is pretty simply by just taking 1.5 and plugging it here into my actual v of t formula. So I'm going to just say v of 1.5 would tell me how tall this first rectangle is. And then I can see that that rectangle is also 0.5 units wide. Notice I could do the same thing now to find the area formula for the second rectangle. How tall is this rectangle? Oh, well, this is v of 2, right? If I plug 2 into the function of v, I would figure out how tall this is. But of course, I also still know that it's 0.5 units wide. If I continue this process, I can see the third rectangle's height can be found by taking 2.5 and plugging it into my function, and then multiply by 0.5. And my final rectangle, its height can be found by plugging 3 into my function, and its width is still 0.5. So I can see here then that actually, if I wanted to go ahead and actually crunch this out, this would be really easy. First, I could go ahead and I could take out the value of 0.5, just factor it out since it's in common with all of these. And I can just slowly start to figure out what each v of these specific numbers actually turns into. So notice here that if I was to plug in 1.5, I'm going to get 1 over 2.5. v of 2 is going to get me 1 over 3. Then 1 over 3.5. And then finally 1 over 4. Now, if I was to simplify this down all the way, and you could use a calculator to kind of help you with this, but you could see that these are going to be able to be turned into kind of the following fractions. Let's see, this would be 2/5. I have 1/3 here. This would be 2/7, and this is 1/4. And you could double check me now by actually seeing what we get if we if we add all of these different fractions together. Well, we're going to get some really, really messy value. It's going to have some sort of large denominator that's going to have, all these different values in here as factors. So actually, I'm just going to go ahead and jump to what it would look like if I just actually crunched out this entire value here. Well, if I rounded that value off to several places, you could see that I would get a value that looks like this. And again, you could use a calculator to double check me. But I think I end up with a value of like 0.6345. And so we could reach the following conclusion. I'll state that we can estimate the distance traveled can estimate the distance traveled by the object from t equals 1 to t equals 3 to be approximately 0.6345 feet. And we can also see, based on what we have in the picture, that this is an underestimate. We know that the real area is going to be a little bit more than this because there was some yellow space that we didn't ultimately grab. So hopefully this gives you some idea of how exactly we're planning on estimating the areas of these really kind of awkwardly shaped regions. We're going to be using this concept of filling our space in with rectangles, and by calculating just areas of rectangles, which is really easy to do, we can get a pretty good sense as to what this value of this area might be. And in certain instances, like we did here, we can even classify this as an over or an underestimate.